Hey guys, hope you guys had a good weekend. Today we're going to continue our lecture on EM. First, let's remind ourselves about what the goal of EM was. The goal was to find our best guess at theta hat, where this represented our parameters. And how we found it was through arg maxing theta integral f theta psi conditioned on our data. So this is our data. Remember, our psi was our latent or missing data, and we wanted to integrate over psi. Okay, this f has a lot of examples. It could be our likelihood, or it could be a probability measure. In either case, it ends up working out, and everything ends up working out the exact same way, just different notation. Now, what we saw through EM was running a particular algorithm through two steps. Step one, was an expectation with respect to psi conditioned on the thetas, previous thetas, log our likelihood, okay? Then step two, which was theta t, would equal the argmax of theta over this q function. Okay? Now, all EM is doing is iterating over these two steps. Now the question is Q closed form? If Q is closed form, it's a lot simpler, and I'll show you some of the steps that we'll have for our mixture model. If not, you're going to apply some type of Monte Carlo approximation. Okay? Through our proof, which was the longer part of last class, we showed our result. Our result was that theta t will converge to our theta hat as t increases. We start increasing t a lot, we're going to start getting towards the truth. Okay? And we prove this by showing if we maximize Q, then we limit to our theta hat, i.e. maxing arg, maxing the integral. As a note, we did call this integral We did call this integral just to make sure we're not getting in confusion. F. We did call it that. So this integral and that, just for notation, same thing. So recap, we are integrating over our complete likelihood. So this is our complete likelihood. You'll see that term show up in Casella and Berger. And we're integrating over our psi. Our goal for your homework, because you guys are going to have a homework problem on this mixture problem, is to iterate over these two steps. And I'm going to walk you guys through it in a one-dimensional case. But let's quickly look at your homework and see what Dr. Lehman's going to have you guys do. Hopefully you guys can see that on the... There we go. So here we're at the course. I gotta find my mouse. We're gonna click on the EM homework, which is due April 25th, according to the syllabus. We'll make this a little bit bigger. So your homework is we have a p-dimensional Gaussian mixture. So rather than a one-dimensional, which I'm going to talk about in a little bit, we have a p-dimensional. And your job is to derive these formulas, I'll talk about this in a second, and implement it through a simulation. I'll also talk to you about that in a second. But right here, Dr. Lehman gives you the steps for going over the EM. So this first step is going to be the expectation step, where all you're doing is finding the probability that a certain point would belong to each cluster. We'll get to that when we talk about our one dimension. And then right here, for mu, you're just calculating the mean for the kth cluster. Then you're calculating the sigma for the kth cluster. What's a little bit different from what I'll show you is that for matrices, you're going to have outer products to work out that. So I highly suggest, because in order to do this, you're going to have to take derivatives of vectors and matrices. Go back to your book, go to online, just double check so that when you guys are working out through all the math, you don't get little errors that could take you a while to figure out. It's happened to me, and if you aren't careful, it could happen to you too. I want to make sure you guys are aware of that. So all part A and B are doing is you are going to derive the MLE. So you're going to take the expectation, and you're going to take the derivative with respect to mu and derivative with respect to sigma. That will make more sense in a second, but what's going to be different from when I show you, and when you guys do it, is you're going to have p-dimension rather than one dimension. Here, all Dr. Lehman is telling you is to do a sim study. Now, I'm going to give you a key insight while he's not in here. Sim study, what he wants you to do, he wants you guys to show him when it works well, what are the limitations, and how does it work in high dimension. So when I'm first doing a sim study, I first want to make sure it works. So in this case, what I would do is start with 2 dimensions, or maybe even 1, and make sure my clusters are pretty far apart, and make sure that the algorithm runs really well. Then I would start moving in the means, and I would start playing with the variances to see when our algorithm works well and when it doesn't work well. The second thing, once you have it on the low dimension case, crank up the dimensionality, play with the sample size. He really wants to see what you guys can find out about the EM algorithm through implementation. So for your sim study, these are the big questions. How does it work? When does it work? What are some of the limitations? And how does it work in high D? This is a big question, whether it's EM or other algorithms. We want to know how all of our sims work in high dimension because we're getting more and more data for every problem we have. So this is your homework. If you have any questions, you can always email us and ask us. But really start this early because you're going to make little mistakes. And it's only going to help you get better by starting early and asking questions. So what I'm going to do now is we're going to cancel out of this. And we are going to talk about the one-dimensional case. And then I'm going to show you guys some implementation through what I have done and talk a little bit about coding it up. So let's first start with our problem, okay? So let's remember what our model looks like. For mixture, model. Note, sometimes these can also be called finite. If you are trying to look stuff up, that's another way that you can maybe help yourself. We're going to say that our x's small k, pi k, normal, x conditioned on mu k sigma square k. Now, when Dr. Lehman was showing this at the end of his last lecture, which was last Wednesday, he also added in this right here, this CI. So let me just remind us all of what our notation was. So this capital K is going to represent the number of components. Let me change this up. Number of components. Another word you could use is cluster or groups. It all means the same. Okay? This K right here is representing the kth component. These pi's are the mixing proportions. Proportions. So when I show you some of the data that I've simulated, what that's really going to represent is the heights of our different. So if we had a two-component mixture and pi is 0.5 and 0.5, the reason they both have to be 0.5 is because the sum of the pi k's has to equal 1 for k. Okay? Sorry, I don't know who's trying to get. They have to sum up to 1. If I had the pi's to be 0.2 and 0.8, you're going to see a big difference. And I'll show you guys that when we get there. Next, here are our parameters with respect to a normal. So last time in this type of setting, I was calling it theta. Okay, so if I use theta, it's representing the whole set. Sometimes I intermix them, it happens. This C right here represents the component assignment or label. I'm trying to give you guys a lot of different names just in case you're going through the literature. You can be very well aware of what they're trying to say. For the ith observation. Okay? Now, again, this normal right here, we're using normals because that's what our homework's going to be. But it could be whatever you want. We could have a normal, a Cauchy, a gamma, all in one big mixture. It's really about what you want to do and what you're trying to model. You always got to think about your problem first. So this is our mixture. Now the question that I want to ask, and I want you guys to take a second to think about, pause the video if you can. what is the likelihood? Or, what is the sampling distribution? Nope, I like that. What is the likelihood? Okay? If you're watching the video, I would recommend taking a pause, thinking about it. Okay? If you can't take a pause, sorry, Will. But a common answer that most people will write is this. I actually don't remember it. Is the product over n, because we have n observations. I is going to go from 1 to n. Then pi k 1 over the square root of 2 pi sigma squared k e to the minus x I minus mu k squared over 2 sigma squared k. This is k equals 1. Now, this is a common answer from most people. And I'm going to have to admit, I would also wrote this down when I was first learning this. But there's a huge mistake, okay? The mistake is, let's think about what our likelihood function is on. Our likelihood, also, by the way, so far, wrong. If you're just joining in, this is wrong so far. I'm going to tell you why in a second. Our likelihood is about the parameters of theta and c conditioned on our data. Remember, theta is just our mu k's, our set of mu k's, and our set of sigma square k's. Okay? But in this likelihood right here, we don't have a representation of our c. So what we have to do is add in, get rid of this wrong, so we're about to fix it. We have to add in an indicator function which allows us to tell ourselves, hey, this is part, let me make sure I get my notation right. And tell us what community we're part of, okay? So all this is doing, this is an indicator function where if let me think of how I'm going to do this. If our xi is in the kth component, then this is going to stay. If it's not, it's out. Pretty much. Then this is a 1, else because we're multiplying. So what I'm trying to say is, let's say we have x1. x1 is going to be part of cluster 1. Then we would pretty much be indicating that we're using mu k and sigma squared 1, where you're in the kth component. Okay? Based off this, and based off what our likelihood is, we're going to start the process of figuring out step 1. And sometimes this is the harder part, and as we move on. So we're going to start working on trying to figure out the log likelihood through some steps. Rewrite this out. Our likelihood of theta psi oh, outside, C's conditioned on X is equal to the product N, so we have N observations, and then our sampling. We will do sum K equals, this can be 2, 3, whatever, I'm going to keep it general. Could be 700 if you want. Pi K, which represents our mixing portions, then 1 over 2 pi sigma squared K. E or X multiplied by our indicator function where C of I is equal to K, bracket. Now we're going to do a little bit of algebra just to make this a little bit simpler, okay? So I'm going to make it, to save some time, algebra happened here. Proportional to, still have the likelihood of E. Now we're going to have everything up in the exponent. We're going to have the sum over the N, I equals to 1, sum of the K, K equals 1, log of pi K minus log sigma K. It's going to be sigma because I'm getting rid of the square root. Also notice this square root of 2 pi is no longer in there. It's proportional because likelihood is going to be proportional. Minus xi mu k squared 2 sigma times, again, our indicator function. Bracket. Again, just to let you guys know, this long formula right here is to the exponent. Alright? The reason why we did that is for this awesome step right here, where we now do the log of the likelihood, and we now just have this big function, which I'll write out one more time. Log of the pi k's minus log of the sigma k's minus xi times our indicator function ci equals k. Okay? So now we have the log likelihood. And what we're going to do from here is just take an expectation. But we got to remember what our expectation is too. Our expectation, step 1 of EM is Q theta t minus 1 expectation of the log likelihood, and our expectation is to psi given theta t minus 1. Okay? So we have to ask ourselves, where is, oh, not size, C's, because C, which is our labels, which is also our component assignment, making sure you guys get all the verbiage in, is our latent variable. We do not get to see our C's, okay? And so when we're looking at this log likelihood, and we're trying to find where the C's are, they are all represented in here. And that is why we needed to add this component here to make sure that our likelihood was proper. Okay, so let's just take an expectation and we're going to keep on going. All right. So, expectation of our log likelihood. Pardon for my shortness of hand there, you guys. Now, if we're going to take this expectation to it, we have to recognize something. Since it only appears here, our expectation can carry all the way until here. So rather than putting expectation and writing this big formula, I'm going to shortcut it a little bit and go nk log of pi k's minus log of sigma k minus xi minus mu k squared all over 2 sigma squared k. Now times, this is where our expectation is going to come into play. Expectation of an indicator function. Boom. Okay? Now while I erase this board, for you guys that are, I want you guys to think about what is the expectation of an indicator function. Okay? I'll let you guys dwell on that for a little bit. So, if you guys were here, hopefully I would get some answers. But the expectation of an indicator function is just the probability of that event. So, one way to write it here. Expectation, again with respect to C, trying to be as clear as possible, of our delta, Ci equal to K, is equal to the probability of observing that cluster assignment or that label. Talk about that in a second. Given all of our data, given all of the pi k's, mu k's, and sigma k's. The reason we came up with that is just through Bayes' theorem. Okay, so Bayes' theorem allows us to have this, and what this represents, a good picture of this, I've always really enjoyed this picture for this, is let's say we have our data. We are given the data, and we're given our parameter assignments. So, let's say this is one community, or one cluster, or one component, and here's the second one. And let's say I tell you, this is our x we're going to be looking at, x1, okay? All we're going to do in this step is find the probability that this x, where, sorry, that's not supposed to be an n, I, okay? This x1, the probability it would lie in this community, or this cluster, and the probability it lies here, okay? From seeing, we can see that it will lie more in this. So all we're looking for is we're trying to derive or figure out the probability that for each point, the probability it lies in each cluster, okay? So let's look and take a couple more steps. Now, this is just going to be the probability, apply some Bayes, probability of xi, right, given Ci k is equal to k times the probability CIK is equal to K. What this CIK is, let me make sure I'm explicit. CIK represents the label for the ith observation and kth component. So what we're representing right here is the probability that xi, so maybe x1 in this case, given the it is in the kth component, or maybe component 1, divided by the sum of the probability of xi condition, because this is going to go from CIK okay, boom. All this is saying, again, I know I keep repeating myself, but I think it's really good because this was the hardest part that I had when I was first learning this, is for x1, we're going to find the probability it's in this cluster. For x1, we're also going to find the probability it's in this cluster. Okay? And what this is going to represent, we're going to keep going, is pi k times the density of it being in the normal, mu k sigma squared k, divided by the sum, pi k times the normal. Ooh. This is k to 1. For simple notation, this is still the expectation of our delta function of Ci equal to k. Another way to write this and think about this are the weights. And so when Dr. Lehman at the end of his discussion started talking about weights, and I believe in his homework it is pi ik, we can look again right before we leave. So a way to look at this would be the weight for ik. So what is the weight of the ith observation in the kth component in this sense? And so this is the expectation step. And so in your code should be 1 or 2 lines. And this would be your step 1. Step 1, figure out the weights. All right? Now we have to move on to our second step. Okay? So let's think about what our second step is going to be. Our second step, we're going to keep that. We're going to write this right here. Our expectation of our log likelihood is going to be equal to pi k times our normal at that the sum is over the k's, normal, and a way to write that down is our weights for I. Okay, now I'm going to come over here, and I'm not going to go through all the derivations, but I'm going to kind of highlight some of the parts. Okay, so I think we're going to take it through the mu estimate. Okay, so now our second step, EM, is to find theta t. In our case, we're going to replace theta t right now with mu t. And we are going to arg max over our theta, or our mu, k. Another way to write this would be to go derivative du k. Either way, depends on how you want to look at it. I like this notation better. We're going to sum. We're just writing our likelihood right now. Okay. Log of our pi k minus log of sigma k minus x in mu squared. And originally, we had the indicator function here, but now we're going to replace that with our weights that we had. So our weights, because we just found it in this step, so let's use it. So what we're going to do when we are taking the derivative, again, when you're doing your p-dimensional case or multi-dimensional case, go and find your cookbook of derivatives. It's going to help you and save you some time. So, quick step is I'm going to take the derivative, kind of simplify this just a slight bit, because we're only going to be taking the derivative over this chunk. Okay? When you take the derivative, here's the, let me make sure I get my indices. Okay, so you're taking the derivative with respect to mu k. So if you think about it, we really want to take two steps in a sense of taking the derivative with respect to mu k1 and derivative with respect to mu 2. What we would do is take the derivative with respect to mu1, set it equal to 0, find the result for mu hat 1. Take the derivative with respect to mu2, set it equal to 0, find what mu hat 2 is. But since they have the same formula, pretty much what I'm going to do is I'm not going to worry about the k. So during this derivative, I'm pretty much going to say I don't need to worry about the k. I just need to really worry about taking the derivative with respect to mu. Because once we have it, we know our next step will encapsulate it. So, or here's a better way. We'll do mu1. Let me just take a step back and we'll do mu1. And we're going to take the derivative with respect to mu1 here. It's going to be the sum So what I did here was I removed this k. Pretty much in my head I did the sum, so I had the mu k1, mu k2. Take the derivative with respect to mu 2, it's a constant, goodbye. Or it's a constant 0, goodbye. So we have this, we're taking this step, and we have this. So you can set equal to 0. Once we do that, we put our little hat. And we end up finding finding that mu hat 1 will equal the sum of xi weight I1 over the sum of weight I1. So you have that. So it's a weighted average. Now, the question you always want to ask yourself, does this make sense? And so if we take a step back and we think about it in a one component mixture is just a normal. This weight would always be 1, so it'd just be x times 1, and then the sum of n1s is 1, so you have x bar. So this answer makes sense. Okay? You can do the same thing for taking the derivative with respect to mu2, but in general, mu hat k is equal to the sum of xi weight I for whatever the k is, sum the weight k's. Okay? This makes sense in 1D, so, or one component and 1D, so it makes sense. For the, erase this. I'm going to abbreviate the sigma just slightly so that I can get to the implementation and kind of show you guys what that's all about. So if we were going to do estimator for sigma squared k, we would get something like this. We're going to take the derivative with respect to sigma k. We're going to have the sum of the n, sum of the k, that's I, equals 1, k equals 1, minus log sigma k times our weights minus xn mu k squared all over 2 times our weights. Okay? All I did was from the likelihood function, log likelihood, I just took out the things that didn't have the sigma k's. And again, with the mu where I only focused on one of the mu's, I'm going to do the same thing because it can generalize. And so I'm going to do the more general and do the more general one. So what you'll get if you take the derivative with respect to any of the sigma k's. So let me write that down. Derivative to respect of any sigma k's, you'd get something like this. R, I, K, sigma at k, because I'm going to set this equal to 0 in a second, plus xn minus mu k squared sigma to the 3 k times to the k. Okay? Then you're going to do a little bit of math, and you will get losing my markers.